Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog. This evening, we are sponsored here in the Department of Astronomy at Boston University. Thanks very much to the chair of the department, Dr. Teresa Brainerd. And we'll be here next month as well, and very much appreciate your company. This is a lecture series. It runs throughout the year. The two this summer will be on astronomy. Tonight, our guest is Dr. Andrew West, and Dr. West is an assistant professor of astronomy here at the BU Department of Astronomy. He received his PhD at the University of Washington, and then after a postdoc at MIT, joined the BU department in 2009, where he's now director of graduate admissions. Dr. West specializes in M dwarfs, also known as red dwarfs, the tiny stars that amount for the bulk of the star population and that are distinct because they seem to burn forever. In the popular lore, the association, many of you probably know, is with Superman and his home planet Krypton, which orbited a red dwarf. And so it came into science by Superman. I don't think Dr. West will be enlightening us about the origins of Superman, but he will give us a much better understanding of the significance of these M dwarfs today, how their structure, their kinematics, and magnetic fields add up to big science. Dr. West's work on M dwarfs has been praised for its innovative use of the huge data sets of the Sloan Digital Sky Survey to determine the ages of the M dwarfs. His research is leading to an explanation of their very long lives, which was a major question, and together with their other unique features, the work will provide an explanation of the essential insights into life cycles of stars in general and the evolution of galaxies, plus the potential of these kinds of stars for planetary systems, a thing that he will address because it's been of great interest in the press. Okay, in addition to his commitment to great science, Dr. West is also a dedicated teacher and mentor, one who's concerned to encourage students and to increase ethnic and cultural diversity in the scientific community. He's also committed to raising public awareness of and support for science. We very much appreciate his contribution to better science education and better public awareness of science, and we thank him for agreeing to talk with us tonight. And it's a great pleasure to welcome Dr. Andrew West.
Nice. All right, so hopefully you can see. Well, thank you very much. Thank you very much for inviting me. I'm going to be telling you today about some of the smallest stars in the galaxy, and hopefully by the end you will agree with me that we can get some big science from these very little stars, and maybe you'll understand my subtitle too, which is more than just the fact that I like Volkswagens. Happen to have owned a few in my history. I would like, before I start though, I'd like to, lest you should believe that we do this all as individuals, I would like to kind of acknowledge some of the collaborators that I've had. At the bottom, I've highlighted some of the many collaborators whose work specifically led to some of the things I'm going to show you in this talk. And then I'd like to especially give a big shout out to my research group here at Boston University, and that's these 11 people now here. 11 people. So thanks to them for continuing the great work for finding big science from little stars. I start many of my talks with this image. It's a galaxy. Let's see if we can wish I could get these down a little. There, that's so much better. This is an image from the Sloan Digital Sky Survey. This is a nearby galaxy. It's a beautiful image. Most of the images of little stars are not as beautiful as this, although they're beautiful in my own heart. But what I like is this demonstrates one of the things that we get when we do large surveys. I'm going to tell you a lot about the Sloan Digital Sky Survey. It's a deep survey looking out to the far reaches of the universe. But when you look out into deep images of the universe, you have to look through our own galaxy. And when you look through the galaxy, there's lots of little things in the way. So if you look really carefully, you'll see all these little dots. They're mostly red. There's a few kind of blue ones, but they're mostly these little red dots. People have referred to these as vermin. People have referred to these as the scourge of the galaxy, the scourge of people who want to actually study nearby galaxies, and there's those little red dots. I was just at a conference where they called them the pimples, the zits of the Milky Way, because they're red and they're little dots that get in the way. But these are actually what, this trash is what I have, at least in the last several years, used as my treasure. Because in order to do these big surveys, you actually have to find all these little stars. And so this kind of is a theme for the rest of the talk. Wanted to give you a couple guiding questions rather than kind of an outline of where I'm going to go. Just a couple of guiding questions that guides my research and my group's research and also guides this talk. And that is to show you that we can use these little tiny stars to answer things about galaxies. If you're interested in galaxies, we actually, using these large data sets of very small stars, have actually made the best maps of the structure of the local galaxy. We've made the best measurements of the movement of the nearby galaxy. So we're actually doing galactic science with stars. We can also do some evolution things. So I hope to kind of convince you of that question. And then there's some other things that will tie into that, but it's a little more physics. It's what are the processes that give rise to magnetic fields? We all know about magnetic fields, whether you stick a magnet to your refrigerator, or you use a compass, or you feel protected every day by the magnetic field of the Earth because there's solar particles coming in. You probably don't think that way. Well, some of the students in the audience might. But how do we set up magnetic fields in these very tiny stars? And what are some of the resulting observations? So any good astronomer would start a nice talk about stars with the Hertzberg-Russell Diagram. This is a classic plot in astronomy. It is a plot of a star's brightness or luminosity, how bright it is, with bright things at the top and dim things at the bottom, versus its temperature or color, which really are the same thing, at least for what we're talking about here. Is blue to the left, so hot things are blue. Over here is cold or red things. It's opposite the way your faucets go. If a physicist had made the faucets, they would have reversed it. So you'd have hot being blue and red being cold. So you've got red stars over here, blue stars over here. And most stars, while they're actually spending their normal lifetimes, they're actually living on what this is called the main sequence. These guys are turning their gas, their hydrogen gas, into helium. We're not going to go into detail of that, but they are spending most of their lives in this spot. And you can see there are big, bright blue stars, and there are small, dim red stars. And you can actually see that this graph is multidimensional. It doesn't just have luminosity and temperature. You can see the sizes of the stars give you an idea that these stars are physically bigger. These stars are actually physically smaller. And you can actually also notice another thing. There are a lot more of these stars than there are these stars. All right? They also are divided into this little numeric category that you may have heard. In the introduction, we heard that I study M stars, or M dwarfs, these stars right here at the end. They're under this banner of M. All right? These are referred to as red dwarfs because they're red, or they also are called M dwarfs. And I'll use those fairly interchangeably. I also may use the term low mass star because these are also very low mass. somewhere between 1/10 and it's half as massive as the sun, which sits right here, roughly, actually right about there. All right? These letters have a fun mnemonic that many of you may have heard many of them. My favorite one is, only boring astronomers find gratification knowing mnemonics like this, yeah. All right? And it's like extra dorky, right? Because knowing and mnemonics are both silent letters, right? So you have to know mnemonics is spelled with an M. Many of you may not have heard of L, T, and Y. Actually, L's are real, some L's are real stars. T and Y dwarfs are actually brown dwarfs. They are failed stars, stars that never became stars. They were almost big enough to become stars, but they never did. And the Y dwarfs were actually recently discovered. In fact, I think the paper hasn't come out yet, so I'm giving you inside knowledge. There are Y dwarfs. They have now been discovered. So there's a whole new class of stars. And each of these can be divided into numeric subclasses. And my students, who I see in the audience, know all about this. You can have M0s, M1s, M2s, M3s, M4s, M5s. Each of these gets subdivided. In science, we like to subdivide everything into many, many categories. There's one other really cool aspect of these stars. So not only they're dim, they're really dim. You can see they're like a 10,000th as luminous as the sun. So they're really dim. They're small, they're puny, they're not very massive, they're cold, but they're super numerous. And it turns out they're really old, or they live for a long time. We heard that in the introduction. These stars, these things live almost no time at all. These guys live essentially forever. When I tell my students this in class, I liken it to a car. And I'm going to tell a story that my father, who's in the audience, hasn't heard, but it actually relates to him. When I was in high school, he drove a car that looked something like this. It was a T-top Camaro. And it was something like a big O-Star. It was really fast. I knew because I was a teenage driver. It had a giant gas tank, but it got really crappy gas mileage. So essentially, you would drive it really fast, and then you'd have to refill it. So that's more like an O-Star. I must have been destined to drive, or to study M-dwarfs, because that's what I drove in high school. A car that, if you're lucky, you could get it going 60, maybe 65, kind of shaking apart. Believe me, I tried. Had a tiny little gas tank, but it could putter all over. These stars, O-stars, have lifetimes of, millions of years. Very short astronomically. Remember, the universe is about 14 billion years old. These have lifetimes that we think or might be on the order of hundreds of billions to trillions of years. We think, because we can't observe that. The universe hasn't been around for long enough. Essentially, every M-dwarf that has ever been born is still alive, barring catastrophic destruction. And that's a whole other talk. I now kind of have sold out a little. I drive probably a G-dwarf. I don't know. We could debate what it is. G-dwarf, maybe. If so. Volkswagens of the galaxy. Why would you want to study these things? I mean, come on, they're little red dots. They're not these beautiful galaxies. They're just these little red dots. Well, one reason is there's a lot of them. Right? There's a lot of them. Our galaxy has 200 billion stars. 70% of the stars in our galaxies are M-dwarfs, that one subclass. So almost all the stars. How many can you see with the naked eye? If you go out on a really clear night, well, not in Boston, but go out to Western Mass or something and look out in the night sky, how many can you see? 0. It's debatable. I see one of my students saying 1. It's debatable. Some people call it a K7. Sorry. So it's maybe 1. 0 sounds better. But here is just a small cutout of the sky, and you can see tons of these little red dots. Again, deep image of the sky. If you turn on your telescope, even get out binoculars, you will begin to see many of these little red dots. And almost all of them are little M-dwarfs. Why else? Well, this one's a really hot one. Turns out planets are probably pretty common. For the last 15 years or so, astronomers have been finding planets around other stars. It was an extremely exciting discovery. Many of you may have seen that in early February, the Kepler satellite announced that they had found more than 1,200 planet candidates. Now, we could have a whole other talk about what exactly that means, why they're not real planets. They have to be followed up with telescopes and have specific observations. And it turns out, actually, we don't have enough telescopic resources to follow up all of these candidates. So we'll never know, or at least we won't know anytime soon, if they are all really planets. But turns out, we looked at a bunch of stars, and guess what? Found a bunch of planets. Turns out they're pretty common, and we found them around M dwarfs. In fact, here is an artist's rendition of a planet around the star GJ1214, or 1214, which I'm sure you guys all know. It's a nearby M dwarf. And this is a planet that was found around it. So if you have 70% of the stars in the galaxy being these low-mass red dwarfs, you might think that, they might be the most numerous hosts of habitable worlds. And it turns out we learned even more from Kepler. I'm going to show you that. Very few kind of science plots, but I thought this one was so spectacular. I made my students last semester just kind of memorize this and beat it down to them in death because it was great. This is a plot of the number of planets, or the percentage of planets, number of planets per star. So if you had and this is the stellar temperature. So essentially what this is the percentage of planets per star for stars over here are high mass stars or high temperature stars. These are low temperature stars. What do you notice? The low temperature stars, and the different colors, let's concentrate on the yellow color, which is planets that are 2 to 4, this RE means Earth radii. So are about twice the size of the Earth. So these are small planets around small stars. There are more small planets around small stars than there are small planets around large stars. So an initial result. So the takeaway is small planets, at least close-in ones, that's where they have kind of a complete sample, are more common around low-mass stars. So this is a reason why you might actually want to study these things. These are likely the most common planet hosts. There are a few big differences when we want to talk about planets going around a low-mass star. One term that we throw around is the habitable zone, and astronomers define a habitable zone as the zone in which liquid water can exist. You can imagine if the Earth was further away from the sun, it would be much colder, right? It'd be much colder, and the water on Earth would freeze. You could imagine if Earth was a little closer to the sun, the water would boil away or evaporate. And so astronomers define a habitable zone. This is a plot of different stars, starting with, here's the sun. It's the mass of the star relative to the sun. So this is the sun. Here's a star twice as massive as the sun, and here's a star half as massive as the sun. And here are all of the planets in our solar system, although there's one here that's not a planet anymore. Again, the topic of a different talk. This is now a dwarf planet. But you can see here's the zone where liquid water can exist. If you move a little too close, it's too hot. If you move a little too far away, it's too cold. But of course, you can see as you go to different types of stars, the more massive stars, which are hotter, burn brighter, the habitable zone is further away. When you get down to lower mass stars, the stars are cooler and dimmer, and so that habitable zone moves very close. And so in fact, you actually have to have, if you want to have a habitable planet around a low mass red dwarf, it actually has to be quite close. Keep that in mind too. So I want to change gears from the reasons why we might study to show you some of the things that we can do with red dwarfs. And one of the things is to think about, again, I said one of the main questions that I wanted to address is what can we learn about the galaxy? So here is just a photograph, a photo of the Milky Way, as you might see it from Earth. And I'll show you this in cartoon form, but you may remember this, and if not, well, you learn it now. That the Milky Way is a spiral galaxy. It looks something like a like a Frisbee. I have a bunch of these in my office, so I brought one down. And we live actually about in the middle of this disk. So when you look up at the night sky and you see this, you're kind of looking through the plane of this Frisbee. But that plane is made up of billions of stars. So you see them all kind of mashed together, and they smear out. Your eye cannot resolve the individual points. And so it looks like this nice cloudy, milky substance that people called the Milky Way. But it's really looking through billions of stars. If you look above here, up here, you're looking up above the Frisbee. If you look down here, you're looking down through the Frisbee. And if you look along here, you're looking all along the Frisbee. And so you look through all of those billions of stars. So what can we learn about what the Milky Way looks like? So here's a cartoon of that, if my Frisbee didn't help. Here's kind of the galaxy. Its basic shape is a flat disk. Here's what it looks like looking down on the Frisbee. And here's what it looks like looking edge on, we would say, on the Frisbee. The sun is roughly about 2/3 of the way out, depending on where you define the edge and what distance where the sun is from the center is. And there's, maybe you put a softball or a baseball in the center of the Frisbee, and we call that a bulge. But the sun lives about right here. Turns out, this is another image from the Sloan Digital Sky Survey of a nearby galaxy. Turns out stars form in that disk, in that Frisbee, in the plane of the Frisbee in the galaxy. They form in this thin layer of dust and gas. And so you can actually see that very nicely in this galaxy. This galaxy is aligned really nicely edge on to our point of view. And so you can actually see this layer of dust here that's actually not the absence of stars, but it's actually the presence of dust that is blocking the light coming from this galaxy. And it's actually new stars are forming right in that very small plane. It's a very thin layer in most galaxies. And you may have seen some of these beautiful images that the Hubble Space Telescope took. This is one of the Eagle Nebula. This is a very zoom in our own galaxy of a region near the plane of the galaxy where there's a lot of gas and dust that is now condensing to form stars. And so these are pillars of gas and dust. And if you actually look, you can see a little bit of light starting to shine out of the tips of these pillars. And those are new stars that are beginning to poke out of these columns of gas and dust. This is all happening near the plane of galaxies, including our own. If you look even closer with the Hubble Space Telescope, you see these are called propylids. These are in one of the places where stars are forming in the constellation Orion. And you can actually see the beginnings of disks that we think might eventually form things like planets. So there's a lot of exciting things happening in our own galaxy. But all of this is happening again near that plane. People have actually used computer simulations to help us understand the process of star formation. These are simulations from Matthew Bate, who's a professor at Exeter. This is a simulation of a gas cloud. And the gas cloud is collapsing under its own gravity. And you can actually see eventually little pockets get hot enough for individual stars to turn on. You can actually see little individual stars being formed. It's all done with a computer. You can watch as this star formation takes place. And what scientists like Dr. Bate do is then take these simulations and compare them to observations of star-forming regions and brand new clusters of stars that have just formed. And then they can actually tune their models, and they can help us understand the physics of how you actually get these star formation processes. So this is a brand new star cluster that's being formed, in this case, inside a computer. And there you go. So stars form by this gravitational collapse in the very thin part of this galaxy, and yet you should hopefully notice something about this galaxy. It actually has thickness. there are stars. All this light here is coming from, again, billions of stars in this galaxy that your eye can't resolve each individual point. And so, but I told you that the stars formed in that little thin layer. So somehow the stars had to get from the thin layer to the outside. We see that same thing in our galaxy. They don't stay that nice thin way forever. And the way that happens is a process called dynamical heating. So you can imagine you have all that gas and dust sitting in the galaxy, and it's in that nice thin layer. And there's a lot of it. It has mass. It's got a lot of mass. So that when a star passes near, these are all little clouds of gas. It's my PowerPoint skills. As the star passes through, it gets really close to one of these little clouds of gas, and there's a gravitational tug that gives it a little bit of a kick. So stars gain a little bit of velocity. They get a little bit of tug every time they pass kind of through the plane of the galaxy. All right? So that happens, and it happens over and over again. Takes a couple 100 million years for the sun to make an orbit. That's not a short time, but it's not a crazy long time. So the sun itself has kind of passed through and probably interacted itself with some nearby clouds of gas or other stars. There are all these kind of things that can help dynamically heat. If that doesn't help, maybe this will. This is, hopefully you guys know it's a swing set, but let's pretend for a second that we know that all the kids start their lives on the swing set with the chains up and down. Let's call that the plane of the swing set, just like the stars were formed in the plane of the galaxy. All right? And as the kids get on the swing set longer, they probably have an adult or a sibling or someone who gives them a push. And as they pass through the galaxy, as the plane of the swing set, let me say, they get another push. And that allows them to swing further. And you give them another push, and they swing further. And that way, you could have the notion that when you took a snapshot, the kids that had achieved the furthest distance, were swinging the furthest away, or moving the fastest, had been there longer because they've received more of those pushes from their parent. And the kids who were closer to the plane, on average, probably haven't received very many pushes. Now, astronomers will sometimes do statistics with 4 objects. That's generally bad. Generally not a good thing to do. And so instead, we don't use 4. We use many of these because, of course, someone in the audience could make the argument that this kid, who I would say maybe hasn't been swinging very long because he's really close to that starting point, someone could say he's just passing through. All right? This kid's probably been on the swing the longest, though, you could say, again, on average, because he's swinging way away from that middle plane. But instead, if you lined up, I don't know, tens of thousands or 1 million of these kids, it'd be a really long swing set. But then you could actually say this statistically. You could say, yeah, the things nearest to the center are actually younger, have been swinging for a less amount of time, a shorter amount of time, and the kids further away have been swinging for a farther away, longer amount of time. So we need bigger samples. We can't do this with 4. Again, that would be bad. So when you're married to an archaeologist, as I am, you get some crazy notions sometimes because you talk about what you do. Actually, you get to sometimes go on digs. This was me digging in Alaska last year with my wife. But as I look in the house pit that we're digging, this is an old hearth, an old place where they had a fire 1,000 years ago or so in a house pit. But you notice all these like stratigraphic layers. So after many years of being with my wife, you get some ideas about how you might apply archaeological concepts to astronomy, which sounds kind of crazy. But I came up with this notion of galactic stratigraphy, which is just like the swings, remember? Just like in archaeology or geology, you have these layers that we saw very clearly from that Alaskan house pit. When you have stuff near the surface, it's the youngest material. It was been laid down most recently. And as you dig deeper and deeper, you're going more and more into the past. All right? It's a concept that geologists use, that archaeologists use. Well, we can do the same thing with a galaxy. Remember, we know that stars, here's another picture of a pretty nice edge-on galaxy. Stars form in this layer of gas and dust. They slowly get kicked out. They get those pushes, just like the kids on the swing set. They move slowly away from the center as they live longer in that galaxy and get more of these dynamical kicks. So stars that are further away from that starting point are likely, on average, older. And they can, in galaxies, they can actually go both directions. It's a little better than archaeology or geology, where you can only go down. Here you can go up and down. So if you're near the center, you're younger. If you're on the top or the bottom, if you're away from that starting point, you can go older. And we've actually come up with ways of attempting to calibrate that. And a lot of my research is actually designed to actually calibrate this method. But I'm going to have you take it on some level of faith that we can actually do this pretty well. In order to do that, there is one caveat. You can't do it with 4 kids on a swing set. Can't do it with 4. We can't do it with 4 stars. You need huge data sets to actually do this in any reasonable statistical way. And so one of the data sets that I use comes from this observatory. This is Apache Point Observatory in New Mexico. There are many telescopes on site, including a 3.5-meter telescope. This is a little 1-meter telescope. But most importantly, at least to my life so far, is the Sloan Digital Sky Survey telescope, which sits right on the edge of this mountain. There's actually a pier that goes right off over the edge of the mountain. Actually, you see the solar telescope in the back. It's on this site. So here's a zoom in and people for your good astronomers for reference. I've lost my laser pointer. Don't look at it. It's fine. I think there's a, well, that's fine. So this is the Sloan Digital Sky Survey telescope. And if you look in the background, you can actually see White Sands, New Mexico, the national park there. So this is a beautiful, beautiful site up in the mountains of New Mexico. This is a 2.5-meter telescope. That crazy stuff on the edge of the telescope, which doesn't look like your typical telescope, is wind baffling because it's on the edge of a mountain. The winds come through there, and that's to actually help stabilize it against the wind as it comes through, so it can still take nice, stable images. Sloan's Digital Sky Survey has been an extremely impressive device for astronomers, studying all sorts of things. It was actually designed not to study little small stars, but it was designed to study the far reaches of the universe, to understand the structure of the universe, to look for some of the most distant objects in the universe. This is the camera on the left, and you can see it actually has 30 different little units in the main units, and each kind of has a different color. Those are filters, so we actually know which type of light is kind of coming through the telescope. And then there's 30 different ones, so we get a very wide picture of the sky every time it's looking up. To date, which is actually still ongoing in its current, its own form, there is almost 1 billion unique detections. It has discovered almost 1 billion objects in the universe. Just the images alone, if you wanted to grab all of the images, would be 50 terabytes of data, if that makes sense to you. Some of the new upcoming surveys will do this in a night or two. So this is actually, sounds like a lot, and it was a lot when this began, but now it's actually turning into a very small amount of data. Half of those detections are stars. So a huge amount. Again, when you look through a galaxy, you actually get a ton of stars. If you're interested in getting more information, I've put the website below so that you can grab more information. Just to give you a sense of the scale and the quality of the Sloan Digital Sky Survey data, this was put together by professors Mike Blanton and David Hogg at NYU. I'll zoom it out again. This is showing you the extent of the Sloan imaging. It starts on a nearby galaxy. Oh, got it back. And zooms out. You can see all the stars and galaxies. And if you look carefully, you can see there's some kind of hopefully familiar constellation, although it's going really fast. Did people see what constellation that was? It's the Big Dipper. One more time, just for fun. You'll see the Big Dipper as it comes out. 1, 2, 3, 4, dipper. There's the, bam. It also has a spectroscopic mode. This is a technique that I'll explain in a second, where you take the light from its single color or single amount of light and spread it into all its composite elements or its composite colors. This is the way that Sloan Digital Sky Survey did it. It had a big aluminum plate. It was about yay big. It had 640 little holes in it. And it was some guy's job every night to go and take these fiber optic cables and put the cable in the hole, and then put the machine on the telescope. And it was aligned just so that each hole matched up with a star on the sky, and then it pointed to the sky. So luckily, you didn't have to match hole 1 with fiber 1 and hole 2 with fiber 2. There was like a nice mechanism for making sure you know which fiber got put in each hole, or else this guy's job. And this was actually a totally staged photograph. There were other people, graduate students or someone doing that. Of course, just to explain a little what that technique does, most of you have actually experienced this. Even if you haven't seen an astronomical spectrum, you've probably seen a spectrum. You've seen a rainbow in the sky, or you've seen a prism where light comes in and hits a prism, and the prism actually breaks the light into its composite colors. The light actually travels slightly, refracts the light, and it reflects blue light differently than red light, and so it spreads it out into its rainbow colors. And so if you have white light, if you have a nice white light source, that's actually a mixture of all the colors. It's not like when you were in kindergarten and you had all your paint colors and you mixed them all together and you got some brownish, grayish thing. Light's very different. When you mix all the colors together, you get white. And so you can see white light goes in and rainbow gets out. So if you had a really good prism, a fancy prism, or something that we might use called a diffraction grating, you might get, and you pointed it up at the sun, which of course you shouldn't do by yourselves without the right device, you might get something like this. And you'd see red, and these have been all put together onto one graph, but you can see the red light through the purple light, but you notice that things are missing. It's not actually a perfect rainbow. And all of these are what we call absorption lines. These are places where light is missing, where a piece of the sun's atmosphere has actually absorbed specific elements. Some are sodium, like these two lines here. Some are hydrogen, like this line here. Most of these little lines in here are iron, magnesium. So we get to actually see all of these elements in the sun's atmosphere because they actually disappear in the spectrum. And if you're interested in how that works, you can talk to me later. Just to help you see a couple of the plots I'm going to show, instead of showing the colors of the rainbow, we might actually plot this same plot in a slightly different way, where we plot its brightness. Again, here's the bright part of the plot, here's the faint part of the plot, and we plot its wavelength, which is just a way of explaining its color. So things with a short wavelength are blue, and things with a long wavelength are red. So it's this plot and this plot are the same. This is a spectrum of the sun. I've just instead made this the brightness and plotted the color numerically. And you can still see there are places where there's things missing, like hydrogen and iron, calcium. There's places where they're missing, where the sun is absorbing the light. And different stars, all of those different stars that we talked about, the O, B, A, F, G, K, M, remember that? L, T, Y. All of those have different spectra. So here's an O star, a B star, an A star, F, all the way through M. And here's what they look like in that other form. O stars, B stars, G stars. You can see O stars have a ton of their light in the blue. Remember, those were the big blue Camaros. So a lot of their light in the blue. You can see for the M dwarfs, the little red ones, those guys are over here. Most of their light is in the red. They're brightest Remember, the height is how bright they are, is over here where the wavelength is the longest, and they're red. All right. You also notice that if we look carefully at the M dwarfs, they've got all these crazy dips. They look much more jagged. They actually look, I think they look prettier. But they've got all these big dips. These are because the atmospheres are actually so cold on these stars that actually molecules can condense. So it's not just single elements, whole molecules can. So you can actually see here's titanium oxide, here's calcium hydride, here's calcium hydroxide. You get whole molecules that are absorbing the light, not just single elements, because you've actually gotten so cold that the atoms can actually bond together in the atmospheres. It actually makes them extremely hard to do models. A lot of the way that people who study stars that are much higher mass is they say, okay, we know what a star is. It's a big hot ball of gas. We put some elements around it, and we can calculate what it should look like. Well, it turns out you can't do that for the really low red stars. And so we have to come up with a lot of techniques for understanding what their compositions are, what their exact temperatures are, all of those types of things. So using the Sloan Digital Sky Survey, myself and my colleagues have assembled the largest samples of these stars that have ever been created. We've created catalogs of imaging, so images of these stars, of over 30 million of these. And we've looked at over 70,000 spectra of these objects. And actually I have a set of graduate students and undergrads, both here at Boston University and at other institutions, who have actually looked at every single one of these by eye. In fact, there's one student here at BU who looked at just over 19,000 of those by eye. Oh man, what a lot of work. More than I have ever looked at, I think. We've also done some of the really low cool objects, the L dwarfs. There aren't very many T or Y dwarfs. There's only one or two Y dwarfs, I told you. And what I'd like you to know, here's a image from the story of Goldilocks. Turns out, even though these stars are really dim, when you're doing a deep survey of the universe, when you're trying to look to the deepest pieces of the universe, you don't want to use a bunch of bright stars because you're trying to push to really faint limits to find those galaxies and those quasars and the supermassive black holes way out in the distant ends of the universe. If you have a really intrinsically bright star, it's going to be too bright for your survey. It's going to saturate your electronics. So it turns out even those little dim red dots, they're not too bright, but they're not too faint. So you get these large samples of them when you do these deep surveys. So they are the kind of Goldilocks star for studying our galaxy. If you went slightly more massive, you actually don't get any of them nearby because they're too bright. So they're actually just right. So that's our sample. In order to tell you a little bit about our sample, I want to tell you a little bit about some of the specific things happening in the star themselves before we jump to, I think, the one big science result I want to show you. But at first, I need to tell you a little bit about our own star, our own sun, because it's the nearest star to us, and it's what we know about the most. And we will then understand something about the smaller stars in comparison to the sun. Stars like our sun have strong magnetic fields. And actually, they're not really strong, but we notice them on a daily basis because we're so close to them. They manifest themselves in flares. Here's a movie from the TRACE satellite. It's a flare. These are actually all the magnetic field lines. If you ever played with bar magnets in science class and had little iron filings, you noticed there were actually the filings went to kind of circles around the bar magnet. That's actually what you're seeing here. You're seeing loops of magnetic field on the surface of the sun. And this is actually taken in almost X-rays, and you're seeing actually light being actually emitted by X-rays as particles travel along those magnetic field lines. We also see it with sunspots. If you've ever looked at the sun, projected the sun onto another surface, or looked at the sun through a telescope, you actually see it has these little spots on it. these are actually places where the sun is slightly cooler because of strong magnetic field is actually preventing the gas on the surface there from sinking back down and cooling. So it's slightly cooler. Those are spots of strong field. Here are strong loops. Once in a while, you get large flares where the sun throws material out, and that's actually caused by the magnetic fields of the sun. So sun is in has a magnetic environment. It produces some great phenomena like the aurora, the northern or southern lights. You can actually see the Earth's magnetic field lines here. These are charged particles from the sun that are coming in and interacting with the Earth. And you can actually see some of these lines here are actually the directions of the Earth's magnetic field lines as the particles come in, which is pretty exciting. And stellar flares, may cause some problems for extrasolar planets if they don't have, like we have, this nice shield. We have the Earth has this strong magnetic field, which as the sun releases these big particles out into space, those particles get trapped along the Earth's magnetic field lines, and they protect us from a large amount of those high energy particles that might otherwise slam right into us and do all sorts of not so nice things. So this may be something that's kind of important for understanding the ability to have life or habitability on other planets. This is the kind of cartoon of what the sun looks like on the inside. It has different layers, has a core at the inside where all of the energy is made. Then it radiates away light. Radiation, of course, is just, if I'm feeling this light bulb that's sitting right here, I can feel it's hot because the light there's energy radiating away from that. And then convection, the outer part of the sun is undergoing the energy transport mechanism convection, which again you all know because you've seen a pot boil on your stove, right? You heat up the bottom of the pot and the hot water rises to the top. You see the bubbles come up, and then as the water cools, it goes back down. The hot water from the bottom bubbles up, cools back down, and you actually get a convective cycle that heats up your pot of water. Same thing happens on the surface of the sun. How do we know this? How do we know what the sun looks like? And what does this have to do with magnetic fields and all of that? Well, it turns out that we can actually see that the sun vibrates, and it vibrates like a bell. This is really cool stuff. This is called helioseismology. And the sun actually vibrates like a bell. And that actually allows us to look inside of it, just like geologists study how the Earth vibrates during earthquakes, and they can tell what the Earth looks like on the inside. We can do the same thing with the sun. So this is an artist's conception of what the sun looks like when it's vibrating like a bell. And what we see, what we see is that the sun, this is a plot of how fast the sun is rotating as a function of where it is on the surface. This is the outer surface of the sun, and this is the inside of the sun. The sun is rotating very fast, and on all these different lines are where you are on the sun. In fact, here's maybe a better image. Here's a outer slice of the sun. Here's near the equator of the sun. Here's the top of the sun. Here's the outside of the sun. Here's the inside of the sun. Down here, the sun is rotating very fast. Up here, it's rotating very slow. And you can see all inside here, it's rotating at the same speed. The colors denote the speed of rotation. And what happens is right at this layer here, you can see the inside part of the sun is rotating like a ball, just rotating like that. And the outer part, it's fast down here and slow up here. So this is shearing by the equator of the star, and this is shearing by the pole of the sun. And we think that that is extremely important to actually generating and preserving the magnetic field. We call that layer where that shearing occurs the tachocline. That's where it happens, the tachocline. Getting back to the smallest stars, it turns out the smallest red dwarfs or M dwarfs do not have a tachocline. They actually are fully convective. So here's a star like the sun that has radiation on the inside and convection on the outside. The M dwarfs, these little tiny guys, are actually convective all the way. They don't have that shearing layer. And yet we think they have very, very strong magnetic fields. we actually measure that by looking at their spectrum, getting back to the spectra. So here is an image of an M-dwarf spectrum. And what you see here is the blue light, here's the red light. And this is the same star taken at different times. And what you notice is that the red spectrum is much higher here than it is here. And that's because this star has been flaring. It's had a huge flare, just like the sun did, and its outer surface actually got superheated and got a lot bluer. Remember, bluer is higher temperature. So this part of the spectrum got a lot more blue light. And that's because it got really hot during one of these giant flare events, where it spit tons of material out into space, likely. All right, so we see that these stars, and remember, this is due to these strong magnetic fields on the surface of the sun. We think the same thing is happening here. So, summary of red dwarfs. They have lifetimes that are longer than the current age of the universe. They are small, faint, make up most of the stars in the universe. They are fully convective, yet they have strong fields. And in the last couple minutes, I want to show you that we can do a lot by combining all this information and try to learn something about some of their structure and how that might, and their magnetic fields and the lifetimes of their magnetic fields, and what that might tell us about the planets that might be inhabiting these. So like I told you, there were lots of these. These are images from the Sloan digital, very small point of the sky. And what we've done is at about every time, this is a movie, and each time a new frame comes up, it's 2.5 times fainter. And we've identified all of the low mass stars in this field. And you can see, by the time you get to about the 10th frame, well, not every single, but the majority of the stars are those objects. So what can we do with this? Well, here's kind of where we can see these in the galaxy. This is my simple cartoon I made, where I just said, here's the galaxy edge on, and we're going to put the sun here, and that's about the extent of what we can see. So if you took the Frisbee, we can see a little above and a little below. But why you draw a cartoon when you can look at the real thing? So here is a plot of the same, basically I've zoomed in on this region of the galaxy. And what you're seeing is here's where the sun is. And we can look up through the galaxy and down through the galaxy. That would be where the center of the galaxy is. Here it's color-coded by density. So the blue colors are lower densities. The redder colors are higher densities. And what you can see is there's more stars near the midplane where the sun lives, and fewer stars as you go further up. And if you look really carefully, you can see this diagonal slope. There are more stars towards the center of the galaxy, and fewer stars as you go away. And we can do this for millions of stars, tens of millions of stars. We've actually been able to figure out what a precise structure of the Milky Way looks like. What our galaxy, how it's structured. And here's a nice, we've been working with the Hayden Planetarium, the one in New York, the one at the American Museum of Natural History. And here is actually all of the M-dwarfs that were actually only about 1 million of the M-dwarfs, a small sample of all of our M-dwarfs from Sloan. And you can actually see that we're passing through a cartoon of the galaxy, but you can see that there are more stars near the center of the galaxy, and as you go up, you can see there are fewer and fewer stars. You can actually see that structure, that the galaxy has thickness, but it actually has a shape that there are more things near the center, and as you go further and further away, the population of stars drops off. As we fly through the galaxy, you can see that. Of course, stellar flares, like we said, may have problems for life on extrasolar planets. And we saw that these little tiny stars have big flares. But it turns out that not all of them have flares, and they have flares at different rates. This is the fraction of stars in one of our samples that have these flares. These are all M-dwarfs. Remember I said that some of them, we could subdivide the classes into spectral types. So these are what we call early types or slightly bigger M dwarfs. It's like bigger small things. These are smaller small things. These ones are slightly warmer. These ones are slightly cooler. It turns out they're not all the same. These ones, a very small fraction of them show big flaring, whereas when you get to the very smallest type stars in our galaxy, a huge fraction of them have these big flaring events. So which ones would you want to go find planets around? Well, maybe not these ones. These ones might have huge events that flare huge amounts of stuff into the galaxy. These ones have tiny amounts, or very few of them are going to be flaring. So myself and my colleagues thought, why does this happen? What could cause the shape of this plot? We said, well, maybe what we're seeing is that these guys stay active. They stay in this flaring state for a really, really long time. Remember, these stars last forever. Maybe these guys have very short amounts of time they spend active. So we said, we know something. We know about this galactic stratigraphy. We know that if we look near the plane, we're going to be looking at younger things. As we look further away, we're going to be looking at older things. So what we did is we plotted that up. This is just a plot. It's the same plot before. It's the fraction of stars that show this large flaring. This is the vertical distance from the plane. So it's literally as if I put the Frisbee kind of here. Here's things above the Frisbee. Here's things below the Frisbee. And what we saw was that things near the center, where the stars are the youngest, are flaring the most. And as you go further and further away and are tracing older and older populations, the fraction of stars drops down. So older things are less likely to be active. Younger things are more likely to be active. It's kind of, there's a joke, NPR did a little piece when this paper came out, and they said it was like people. That the more you age, the less active you get. I don't know if that's really true, but they thought it was funny. And we see this at all spectral types. So we were able to use our galactic stratigraphy to actually find out something about how long stars stay active. So for the earliest, the smallest type M dwarfs, the active lifetimes are only about 1 billion years, which I know sounds like a very long time. But remember, these live for trillion years, maybe. For these guys, it's more like 7 or 8 billion years. So if the universe has only been around for 14 billion years, and these guys, when they turn on, are going to start frying their planets for billions of years, you might not want to go look for planets around these types of stars. You might want to go look trying to find planets around these types of stars that are only very, very active for a short amount of time. So one of the things that we might ask is, how do you redefine this habitable zone? Remember, I said it was just based on where water is liquid. But what about other factors? What about this stellar activity, this stellar flaring? If you get an M dwarf where water can be active really close, you're bringing that really close to a star that's just then going to flare and fry it. So there may be some other factors that we need to think about in the habitability of planets around these stars. There's a lot of other surveys going on. I've talked about just the Sloan Digital Sky Survey. There's a lot of upcoming surveys, one called LSST, Pan-STARRS, all of these ones, many of which I'm involved in or have collaborators who are involved in. This is research that is going to continue for a very long amount of time with a lot of exciting new data. In fact, like many terabytes a night coming down. So I'm going to end there. Hopefully I have